Okay, let's get started. Any questions? Thanks. You ready, sir? Any questions? Good. So, I guess homework 1 was due last Friday or something. And in a day or two, I will post a second homework set. Okay? And yes, again, you can submit it to your work to TA through email, or I don't know if there is a way to submit it on KLMS website. So whichever way, just communicate properly. Okay, any questions so far? Okay, so you now are happy with quantum field. Hopefully you made a friend with quantum field and why it looks like that, right? So now we will start developing some aspect of quantum field theory. Okay, so we discussed how to think about the free quadratic quantum field theory for real scalars, and also sometimes a complex scalars. And the discussion we will have, maybe roughly week and a half or so, is about the symmetries appearing in quantum field theory. Okay, so Philip Anders, who won the Nobel Prize in, I forget, 1977, 79, right? He said that something like, not exactly, it is only slightly, overstating the case to say that physics is the study of the symmetry. Okay, so it's that much. It's incredibly important, deep, and so far limitless concept. Okay, still one of the modern contemporary research is to understand new versions of symmetry, implications of those new versions of symmetry, and so on and so forth. This keeps happening, so we certainly have to spend some time thinking about symmetries. So, okay, 5, Sum 5, Chapter 5, Section 5, Sum 5. So we're going to talk about symmetries and convergence. So in the first part, we're going to spend time on space-time symmetries. Obviously, you already understand the space-time symmetries because that was how we started the whole discussion, right? There was a Poincare invariance, and then we discussed how to think about it, what is the representation. Modulo, we haven't talked about representation of Poincare symmetry on quantum field yet, but other than that, we already talked about a lot of things. So we will assume there's an action description of quantum field theory. Okay, and then there's Lagrangian density, which consists of a field and its derivative. Okay, then here the symmetry. So we will mostly focus on, we will talk about not just any symmetry, but we're going to talk about mostly continuous symmetry. Continuous symmetries. Okay, so that's the sort of a focus we will take for a while, although we will discuss some of the discrete symmetries as we go along. So what is a symmetry? Symmetry is a set of transformation that leaves physics invariant. Okay, so let's make this statement precisely at the level of action. Okay, so suppose you perform a symmetry transformation given a phi of x to transform the field. But when I say that I'm going to consider continuous symmetry, what that means is that it's continuous. So there is a notion of small transformation, so infinitesimal symmetry transformation. Okay, so that's that's one of the characteristics of continuous symmetries. We can talk about small infinitesimal transformations. So here I want to talk about small infinitesimal transformations, and then I'm going to write it as original phi plus small changes. Okay. In particular, suppose what controls the small parameter is epsilon, then we are going to rewrite this as basically d phi of x, where by comparing the two, the notation capital D of x which is not covariant derivative, you haven't even reached that point. You can think of it as change of phi. Well, I guess we can just with respect to epsilon, and then as epsilon goes over. Right? So that's basically the function. So we're gonna work in the limit where epsilon is very, very small. Okay. Then there is a statement. So then again, we are trying to say that what do I mean by this symmetry? So first of all, then let's ask what happens if we do this at the level of action. So in general, given an action, we can talk about a transformed action. And obviously, if action stays to be the same, that's manifestly a symmetry, right? It doesn't change anything. And if we get equations of motion, quantization of a quadratic theory, quantum field, blah, blah, everything will be identically true, right? So that's obviously a true statement. But in principle, you can allow a shift of action by 2 pi or 2 pi times integer. So up to that point, this is a notion of the symmetry of action. You might say, why this is allowed? Well, first of all, if you do the perturbation theory, right, and then if you do the variation of action and stuff like that, obviously this return just drops out in any of those evaluations. But if you wish, there's another way of approaching the quantum field theory known as path integral. And in path integral picture, don't worry about it if this doesn't make sense. In path integral picture, the primary object that we are looking at is some version of integral of this field, but in this case, classical field. And you probably want to look at the insertions of all those stuff. And then it is weighted by this, either the I action. So you see that if you shift action by 2 pi times integer, obviously it doesn't make any changes. So any of these primary, completely quantum mechanical object doesn't change at all. Okay? That's why 2 pi times integer is harmless from the perspective of quantum field. Anyway, but in our lecture, we'll just focus on this. And one of the reasons is because I'm going to spend most of the time talking about continuous version of the symmetries, and it's unlikely. I don't have a mathematical theorem, but it's unlikely that if you do make a continuous transformation, you ever actually shift action by this very discretized, quantized shift. Okay? So it's most likely that for continuous symmetry, only if it were to be a symmetry, only leaves action just invariant. Okay? So that's the notion of symmetry. What about at the level of Lagrangian? So at the level of Lagrangian, so again, this is just this, right? And suppose now I change the action by s plus delta s. Well, s is s, so here where delta s can be written as e4x variation of Lagrangian, right? So which means that I will vary here Lagrangian to the transformed one plus variation. Now you can ask what types of a shift in the Lagrangian can set this to be 0. Again, I'm just focusing on this without the 2 pi z. And you notice that if this is some total divergence, okay, such that this function, this will be a function of original field and then epsilon, the transformation parameter, and then this if you use the divergence theorem, so long as this goes to 0 at spatial infinity, in space-time boundary, then you see that the action is invariant. So the statement, here I'm just make a statement that what do I mean by symmetry in this class? Symmetry, I'm looking at the case where the set of transformations, the leaves action invariant. In terms of Lagrangian, I'm looking at a transformation of quantum field, in this case actually classical field, that shift action by total divergence modulo this boundary behavior. Okay? Okay. So with this, now I can make a statement, meaningful statement. So there is a useful theorem, probably you have seen in other contexts, either classical mechanics or some other context. There is a theorem called a Noether theorem. Okay? So, so here the statement is that continuous symmetry implies an existence of conserved current. And this is the conserved. It's called the Noether's current or conserved current. Yeah, okay, yes. Where are we talking about? This? Yes? Yes? Oh, sorry, yes. Yes, that's right. Yes. So this will be, I'm looking at this linear indifference, I'm taking a partial derivative and then setting a difference. Right. Any other question? Okay. Good. So, Noether theorem says that if you have, say, action formulation, which doesn't need to be, if you have a continuous symmetry, then there exists a current which is conserved. It has to satisfy this property. So this is a very useful and important implication of symmetry. And so this is, if you wish, as you will see more, classical aspects of continuous symmetry. So here, I'm just stressing out, it is a classical aspect of it. You might say, what do I mean by classical? Like I said, everything is quantum mechanical, right? So everything is quantum mechanical. So if you have things that everything is completely quantum. And if you look at any quantity, especially perturbation theory, there's a piece that comes from, there are theories that doesn't take any classical limit. There's a classical piece and there's a quantum corrections. Okay? So if you want to talk about, for instance, what do we do? So electric charge, not electric charge, but the strength of the interaction between photon and electron. Okay? That strength changes. Okay? And then within the formulation of quantum field theory, that quantity can be taken as a classical leading order contribution plus a small quantum corrections, which is energy dependent, even as we will talk about next semester. So here what I'm saying is that if there's a symmetry, there might be a symmetry that affects the entire quantum physics. Okay? It is fair to say it's quantum symmetry, but this is telling you, I don't know yet, what's going to happen to them, but at least this classical limit will enjoy this property. Okay? And something maybe can happen in between this. Okay? There's this notion of anomaly and so on, so I'm not making any claim about this region, but only thinking about this classical limit. Okay, so let's actually see it, prove it. It doesn't take much of effort. So let's take an action again. Bryan as a phi, del phi. So let me now simplify a bit. Now let's take a look at the variation of action. And then I want to say that this is 0 because I'm talking about the symmetry, right? So this will be e for x. So first of all, we're going to do partial phi del phi. Okay, that's first piece. And then we will have to vary this with respect to derivative of phi, and then derivative of phi. Okay, so I just did an honest derivation. And this is equal to derivative of variation of phi, as we talked about already. So you can do the partial integration by part to say that you have phi and del phi. Well, let me just back it up. And then derivative so in that case, But now, crucially, we have a total surface term that looks like, if you look at it, it looks like this, and then you have to have this. Okay? So far, I just did a literally variation. I haven't imposed anything. Now, previously, now you might notice that, first of all, crucially, delta phi appearing here, as opposed to delta phi, the variation appeared in the derivation of equation of motion is different. So I'm talking about here a continuous symmetry transformation. In particular, let me stress out. We're talking about the lower continuous symmetry transformation. Because I want to check how action changes, right? Under a particular transformation. Global here means that you make a change in the field which look the same everywhere in the space, entire space. In particular, since I'm talking about global transformation, I don't have a freedom to set the variation. So here, therefore, I cannot set the variation goes to 0 as I take a boundary. Okay? Because I'm going to take exactly the same transformation everywhere. So unless it is 0 in the work, it cannot be 0 at the boundary. So this cannot just simply die out. Okay? At the boundary. So if you recall, in the derivation equation of motion, we use the fact that this gives us a surface term evaluated on the boundary, and then we use the fact that this goes to 0, right? I'm going to take a boundary condition for the variation, hence this dropped out, and then we got the fact that this has to be 0 because I'm looking at arbitrary variation, and that gave us Euler-Lagrange equations. That's what we did. But here I'm stressed that this is not 0 on the boundary. Okay? So I cannot just say it is 0. And then we go to crucial difference. Now, symmetry. So this, I want to be equivalent to a variation of action, but the maximal amount I can allow is by total divergence. Right? We talked about. If this is true, then I can view that as a symmetry. 0, then I varied it. Well, okay, so here, parenthesis, I varied the action, and I want that to be up to total divergence, and that is the definition of symmetry we talked about. So then, if you using equations of motion, you might have a question, oh, why are you using equations of motion? Let's talk about it in a minute, but let's first understand. If we use equations of motion to set this part to 0, then I have one divergence piece here, another divergence here as a part of the definition. So we get, therefore, the conclusion that there's something 0, total divergence of. And then let me, before I write that thing, let me just define an object for convenience sake. So one, I already defined it. So right, delta phi already defined epsilon, and then transformation. But this one, I also let me define as epsilon times something else. Okay? So I'm just going to pull out the epsilon factor out of the entire expression. So then I will get d phi minus f hat times epsilon. So I want to consider arbitrary continuous transformation. So now this epsilon parameter is arbitrary, right? And then, in order to satisfy the 0, unless there's a huge conspiracy that there's a fine cancellation, which cannot happen because we're talking about local physics, right? How something happened right here, already know what's happening in the other point. So therefore, we conclude that this gives us a divergence of some object every point in space and time. And so this will be our definition of conserved Noether's current, and that therefore we get the existence of conservation of current. And this is exactly our expression for the Noether's current. Okay, now let me just make a quick comment about the equations of motion. You might say, oh, that's bothering me. Symmetry seems like I can just vary an entire action without thinking about on-field propagation, right? However, I'm talking about the symmetry at the level of action. And so whatever I'm talking about corresponds to the classical limit. I'm not allowed to, by consistency, throw in any quantum picture in this game as yet, right? So it is completely consistent. I'm actually using equations of motion when I do this, make a statement, right? I'm not claiming anything about quantum aspect of symmetry, right? I'm talking about only classical statement. So it's totally consistent. Okay? So that's Noether's theorem. Yeah. Noether's theorem, yes.
How can we use the equations of motion when they're sort of derived in this formulation? I mean, it's like going through other Lagrange derivations, and then you have an extra term, but then you say that you still use the equations of motion. So it's derived. It's like taking, I don't know, the definition of the derivative of cosine or sine x over x, and then using L'Hopital's theorem, which is sort of.
Are you saying that there seems to be a cyclic argument here? Is that your feeling?
Yes.
Okay, so let me clarify. That's why I tried to make the comparison to the derivation equation. But let's just walk through one more time. Let me vary action in the form of a global continuous symmetry transformation rather than taking arbitrary variation. So difference number one. Therefore, surface limit cannot set to be zero arbitrarily. Right? There is an exact rigid transformation I make everywhere, including the boundary. Okay. So far, this is the exact same, right? I haven't done anything. Now, then I say, oh, okay, I want to understand the implication of symmetry at classical limit. Okay, so therefore, at the level of action, that's one side of it, but also, the only thing that I can possibly use the action, in this case, right, is basically free limit. Free limit corresponds to this is 0. So there is this judicious input that we are putting in. I understand the consistency. So symmetry at classical limit. Therefore action, but not just action, but on shell, not the quantum effect. So I'm setting equation motion to be 0. And then I'm saying, then what's left out, right? What is the down implication of symmetry? And that's the same. I don't know if this clarifies to you.
So this is basically just taking the classical limit, and that's why we can insert the equations of motion.
That's right.
To satisfy in the classical limit that this must hold whatever the other is.
Yes. Yes. That's right. Yes. So here I'm just trying to make a more careful statement that just using action is already most likely just the classical limit, right? But I was bothered whenever I see this derivation. Oh, but can you just make arbitrary transformation at the level of action, not just only propagation? But come on, the consistency is that when you say you are doing only physics at the level of action, you're only doing exact classical point shell limit. Hence, it is equivalent to just evaluating the equation of the derivation. Any other question? Yes.
저게 0이 아니라 derivation of action 0이어야 한다고 맨 처음에 찾고 그렇게 해서 그러면 우리가 저 파셜 뮤 F 뮤라는 텀을 생각을 할 수 있었던 거죠. 그러면 저기서 어썸가 중요한 거는 F 뮤가 바운더리에서 죽는가 뭐 중요한 거죠.
Yes.
그리고 나서 이퀘이션 오브 모션을 위에 적용을 해보면 지금 어떤 이퀘이션이 나오냐면 저 F 뮤는 정확히 저거랑 같아야 된다. 저는 보이는 그 위에 있는 저.
No. Okay. Good. So the question is why we are not treating this as literally identical just to do this, but I'm just treating as if there are the two sort of those factors that combine, right, to define the Noether's current. So let me clarify that. So up to this point, I just use the general expression for the variation of action, nothing else, right? At this point, other than the fact that I should not set delta to 0 on the boundary, I haven't used anything about the notion of symmetry as yet, right? So this could have been any variation, and it also validated for any very arbitrary variation, not for symmetry transformation, which does not die out at infinity, right? So far, this is literally an operational definition of variation of action. But now, if that variation are to be a symmetry, I know that had to satisfy this condition. And Okay, I was gonna say make that statement, so let me just do it. So this base is like given if you give me Lagrangian just to compute this, right? On top of that, you know, whether exactly which f mu you get is theory dependent and transformation dependent. So if you actually have a specific expression for the Lagrangian, you can perform actual symmetry transformation and find out how Lagrangian shift by this much. Sometimes it is identical to 0, sometimes it is not. We will go through a couple of examples. Okay, so this is general, and this is exactly Lagrangian shift given a specific theory, and then you combine these two. Okay. Yes.
그래서 오일러 라그랑지 기준 말고 두 번째 텀은
Yes.
결국 파절이 바뀌어 있으면 시험에는 데리베이티브 파이가 바운더리에서 0이 될 테니까 첫 텀은 그냥 어차피 0에서 사라지는 게 아니고.
Sorry, what? This is not 0 at the boundary.
그 부분이
That's what I said several times, but okay, so in the equations of motion derivation, we assume the boundary condition that the variation dies at infinity, and I'm looking at the Burke fluctuations. That was the game we did. Here I'm saying that I'm making a global transformation. Global means that I make the same transformation everywhere in the space and time, including the boundary. So if I do make a non-trivial transformation in the Burke, that means that it cannot be non-trivial on the boundary either. There? Okay. Good. Let's move on. Now, so let's spend a few minutes just appreciating this expression, and then we will actually look at the few examples.
F면은 의미로 적을 수 있으면 게이지 같은 거.
No, it's not. Like I said, if you hand me actual theory, okay? If you give me actual Lagrangian expression, and then if you tell me which transformation I have to do, I will actually perform the transformation on Lagrangian, and then I will actually find out how Lagrangian actually shifts. And from that, I can read off this. Okay? So we will actually compute this explicitly for several examples. Okay? Good. Now, so let's just look at this equation. So let's first look at this, and then this. So this is like J0. And then if you recall, round with this downstairs I we defined to be Laplacian. And then this was actual vector. So we get this equation. Right? And from ENN class or even classical mechanics, you have seen this equation many times. And it is known as continuity equation. So here, it appears as a consequence of a symmetry in the classical limit. Okay, now once we have this, we can construct remember, this is known as a charge density. This is current, right, in that context. We can construct a charge. So this is charge density. So I'm going to have to integrate over the volume to get actual charge, right? So that's what we're going to do. But let me now understand which property this Q has to satisfy because of this issue, right? And because of this constraint. So that we can just integrate this equation over free space. And so if you do that, you get d over dt Q by integrating the first term over free space, and the partial derivative becomes a total derivative because this thing has a time and spatial dependence. But if you integrate, you can pull it out, right? You integrate an entire spatial dependence. The only dependence left out is time, so it should be total time derivative. I'm going to move this side the other side, so equal to minus. So we are doing free integral. And then by divergence theorem, we're talking about d squared s and vector j. Again, on the spatial boundary, by regularity, if this dies out, then we get a conservation law in the sense that total charge, right, of physics happen described by the action has to preserve the total charge in any process you want to look at eventually, right? So this is, if you wish, a notion of a local conservation law in the sense that you can evaluate this property at every point in space and time, space-time point. Now, this gives you a global notion of conservation that the entire thing happening inside has to satisfy this property. Okay? The local version, global version. One last thing I want to say before I actually now start talking about space-time symmetry is that there's ambiguity in defining conserved current. So, so we have this J mu, okay? Well, let me define J mu tilde. So I'm just gonna define a new current by adding such that this thing is an antisymmetric object in U and nu. So then, if you take a conservation equation of this, you get the first piece, you get the second piece. So this is a symmetric, right? This is anti-symmetric. So obviously this delta I, which is therefore equal to the original equation. So the current, conserved current itself therefore has this ambiguity. Sometimes bothering, sometimes useful, freedom to even use of. But let's check what happened to the charge. So charge, again, is defined as integral over the zeroth component. Let's look at it. So what is it? So I'm gonna look at a zeroth component. This is antisymmetric. So I just need to look at the spatial component, right? There's a 0, 0, 0. Wait, how many did I just have? And again, whatever piece you add, such that this doesn't blow up the quantity, which means that this goes to 0 on the spatial boundary, then this piece drops out, and then this is equal to this. Okay, so the current you can actually modify using this freedom, but turns out that the charge, the capital charge, not charge density, remain to be the same. Okay, now, yes?
I just missed exactly how is the derivative, like the whole-time derivative, related to the partial one?
Yeah, so here, question is, why partial became total? Was that the question?
Yes.
Okay, so let's actually look at it. So we are integrating three over the three spatial volume. There's a partial derivative because this is a function of a space and time. This doesn't interfere, so if you pull it out, basically I'm getting an object which was a function of a time and space, but integrating over entire space. The integrated object does not have any spatial dependence. It is only a function of the time. So therefore, it should be just total divergence of object which is only a function of time.
And why does it make sense to assume that the other spatial components are independent of time?
You mean this?
Yes.
So your question is why it is okay to assume that this doesn't have what again?
Time dependence.
It does. In principle, it does.
And where is that exhibited?
Well, I can put time dependence to it. I just didn't write it out explicitly, like so. Maybe I'm missing your point.
But it's just we're taking a time derivative on the left side.
I'm literally take this equation
Yes.
and then integrating over the three volume.
It's not a time derivative, it's just we're taking...
Yeah, I'm literally taking this object and integrating over the three volume. That's what I'm doing. Okay, so the first piece is this, second piece is this. Okay. Yes?
What do you mean by regularity when you set the surface integral to 0?
You mean this piece or that piece?
That.
You mean this piece? So, the regularity, I just mean that if this doesn't die out at infinity with some decay law property, this will just blow up to infinity, right? So what that means is, in order to have any quantity which is a finite and actually talk about physical meaning associated with it, at least I need to impose some quantity goes to 0 and infinity. I'm talking about physical quantity, right? And so whenever this object satisfies that, well, either we can think about that way or we can actually explicitly compute it, as we will do soon. Then, in general, I can expect that this thing will have to go to 0 at infinity. And so if I look at the surface term, it's 0. That's one way of saying it. Or, even simply, I could consider a space-time manifold where there is no even boundary along the spatial direction. Then, obviously, this is also 0. Okay? If you think about the Stokes theorem, right? You have a divergence, and then you look at the surface term. What if there is a surface itself? This is 0. Any other questions?
Should the integral must be performed on the Cauchy surface? Or
Yeah, this is a Cauchy surface.
or arbitrary surface?
Oh, good. So eventually, so this, probably I was debating if I have to talk about that or not. So here I'm literally taking a time fluctuation, and then I slice out a single time slice, and then I integrate over that, and that's where I imagine defining Hilbert space. Another time slice, another time evolution, right? And then Hilbert space is defined on a single time slice. That's where I want to have all the operators and state defined, right? So that's the sense I write down as an actual single time slice integral. However, in modern language, it doesn't matter, and in fact, we can integrate over any 3 surface. That's still valid operation. And there's a topological nature, blah, blah. We'll see how things go. I was going to say a bit about that, if that was the intention of your question. Okay, any other question? Good. All right, so let's talk about the space-time symmetry. So now let's apply this discussion to space-time symmetry. So first, let's talk about space-time translation. In the language of now Lagrangian, and then Noether's count. So to do that, we want to talk about given a field, okay, of x, and then we want to consider given an x mu. I want to consider shift, which is small parameter, and then this. So this represents a small translation. And my notation for E is a basis vector. So do you want to go that way? 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 So this is basically direction indicator. And this is like how much you actually moving towards that direction. Is that clear? So basically smallness is captured by this epsilon, and this is unit vector if you wish. So therefore here, we want to figure out this, and which we can do. So this, and then I have to take a partial derivative of this guy, and then the variation, E rho, right? Okay? Good. Now you can ask, given this transformation, how does the Lagrangian transform? Right? So Lagrangian has a phi and a derivative phi. So you can actually perform it. One way to do that is, okay, so I have to first look at how this changes by this, and then you have to plug in, and then you have to do this. You can plug in this, right? So given this, you can perform this. But there's an easier way to do it. So this is also a function of a space-time point. So if given a Lorentz scalar function, I already figured out how that Lorentz scalar function has to transform under the space-time translation. So this, if you actually work it out, you should be able to find out that the variation is identical with basically that. Okay? And you actually should see the agreement between this calculation and that calculation. Okay? Now, what am I doing here? So I want to consider translation, and I want to figure out Noether's current. In order to figure out Noether's current, you have a two-piece, remember? So we are trying to figure out Noether's current for space-time translation. So Noether's current was this, right? So this, okay, we can write down formal expression. We need to figure out how Lagrange shift under the translation, right? To have this. So that's why I'm computing this. So let's just rewrite this as epsilon. Let me pull it out. Down mu. And then I have a, what do I have? Well, E rho. I had a partial derivative with the upper index rho, but I just write in this way, so I just need to pull it off. Yes? Do you agree? And I can do that because I'm looking at a global transformation. This is just a constant vector, and this is also constant metric. So it doesn't matter whether I pull out the derivative or in. Okay? Good. So we just found out what is the f hat function for space-time translation. Therefore, I can write down the curve. Let's do it. So first of all, here's this. Oh, I can write this. And then we already worked out this, right? So which is E rho, and then derivative phi. So that was how phi transformed. And then we have G. Tell me, what did I have? Mu rho Lagrange. Okay? I haven't specified explicitly which theory I'm talking about, but any theory, right? With the, say, scalar field, for instance. This is the expression. So therefore, I can rewrite this as a two index. Mu rho, mu rho. So I can write it as rho mu, just so that I can contract the rho together. Okay, next to each other. In fact, this expression is known as canonical, there's many names. Energy momentum tensor. Or stress energy tensor, or whatever. So this is that. So therefore, we learned that the Noether current associated with space-time translation is related to a energy momentum tensor. So far, it's a formal expression. Let's explore a little bit. But before that, you might say, "Oh, I'm already scared. You have two indices. Got that, right?" So let me clarify. You have to understand exactly what rho means, exactly what rho means. Okay. So first of all, this rho is capturing what kind of space-time translation I'm talking about, right? So what types of translation am I talking about? So for each types of translation, I have to have a conserved current, right? That's the statement. So for instance, if rho is 0, I'm talking about time translation. And if rho is space-like, I'm talking about space translation. So the first label, rho, indicates that. The second one, on the other hand, is for the conserved current. So we already talked about. So when mu equals to 0, I'm talking about charge density. Yes? And then when mu equals to I, we talked about 3 spatial sense of current. Okay? So this thing has a specific meaning in that sense. Okay, perfect. So I have that discussion here. So like I said, this freedom can be bothering or sometimes useful. So let me just make a short comment about this. So we can actually make use of this freedom to achieve a nice property of this energy momentum tensor. Okay? So for us, so we have a rho mu, and then we can redefine. So let me just write it as a theta mu, or I could have written it as a t tilde rho mu, and then we can define it as this plus. And then I want to have some object. Well, I have to carry both, but then I want to introduce a third derivative such that these two are antisymmetric. So this, I'm using this one to be a minus rho nu mu. So I want to have an object which is antisymmetric because I already have a one derivative with respect to nu, and then when I check the conjugation with respect to mu, I want it to go away, right? That was the design. So I can construct a new energy momentum tensor, stress energy tensor, taking canonical one from the Lagrange derivation. You can add up something like this with the proper, this 3-index object. Turns out, I'm not going to go through any detail, turns out that one can choose this thing such that, first of all, it's possible that you can make energy momentum tensor or is symmetric into those two indices. Okay? This thing is called, oh, I'm certainly terrible in remembering this. Delphi This is the one moment I have to look at it. Delhi, Fante, Rosenfeld. Rosenfeld energy momentum tensor. Or you can choose another version of such that this thing satisfies traceless condition. So this is zero traceless version, okay, which is useful for quantum field theory with the scale invariance. This is by Coleman. Okay, so it's possible. So you can actually use this ambiguity or freedom to get a nice property. For now, let's come back to the translation with this canonical version. Okay, so I'm going to use this canonical version and build up some intuition. So I can give this. So let's actually look at a charge density piece. Okay, now charge density piece. And let's take a look at what is it. And I can even look at, well, let's first look at it. What is it? So this, I have to look at zeroth derivative, phi dot, and then I'm going to look at this, and G0 this. Okay, so far so good. And what is this? That is pi, right? The conjugate momentum. Okay, so now we can actually look at in more detail and build some intuition. So this is a charge density. And then we're going to just define this notation to be capital P rho. Okay? It's an indication of a four momenta. And we will see why this is good, can be interpreted as a four momenta. Okay? So the zeroth component is energy or Hamiltonian. And then we will have a three momenta. Let's see. So this, I haven't shown you yet, but I will show now. But at least I'm just defining first, and I will show this is actually, I think, a four momenta. So let's actually look at it. So what about we look at T0? And that is 0, component of energy momentum tensor. And let's look at it. And that is phi dot minus. And then I'm looking at the 0, component. That's 1 Lagrange. And that's exactly the Legendre transformation of Lagrangian, and which, this. So let me make sure I can fix it. This looks like just Hamiltonian density. Okay, that makes sense. What about the spatial direction? So that's I0, and you have, oh, I have to be careful. Let me just write. And then I have 0, right? That's 0 because this is 0. I'm looking at charge density. So this is a definition minus pi gradient pi. Okay? So you can try to compute the actual integral of that, d3x, and see it is actually give you a sense of 3 momenta, and you can actually compute it, this object. If you do it, I think you should get d3p momenta, 3 momenta, because you have this special derivative, and then if you use the free field, so this is the free field calculation. You have a free field. If you pick a special derivative, you will pull out the momentum. Okay? And then you finish the calculation, and then suppose I use the normal order of the form, you should get dagger. Okay. In that sense, this is literally computes number operator times momentum. This is actually equivalent. Okay? Good. So that makes sense. So for space-time translation, we learned that Noether's current is and as a momentum tensor, and then it actually had the correct interpretation of for momentum. Okay, so that's the translation story. Let's actually now do Lorentz transformation. Hopefully you haven't forgotten everything. Have you? Successfully? So we talked about this, okay? This is metric invariant. And we say that I can look at an infinitesimal version, plug in, we found out that this parameter has to be anti-symmetric, right? And then we can look at a quantum operator, and then we can expand omega alpha beta, j alpha beta. We talked about that kind of stuff, right? So we're talking about this. Now, this quick review reminds you that for Lorentz transformation, which you have 6 parameters, and then you have a 3 rotation, 3 boost. Yes? So compared to the translation story we just talked about, here the parameter is this. Right? So for translation, remember how we did it. Well, I wanted to get not only that we get it, but the Noether current for each parameter. So this is a uniparameter in a sense that smallness was captured by extra epsilon. I can do the same thing. I can pull out the epsilon and then omega alpha beta. So now this is not an infinitesimal parameter per se, but the overall is infinitesimal. This is indicating which direction of a transformation I'm going to do. Okay? And then for any direction, I have to have some sort of tensor, and then contract with the mu for current, right? That's what we just talked about. Not only that, we just speculated it, we actually determined it. So now, what about the Lorentz? What will be the expectation that you will have? So I want to have a Noether current for Lorentz, right? And then you will have omega alpha beta in this sense. And then let's just write down some m. For each of them, I want to have a current. Well, let me put 1/2 exactly for the same reason as this. Because you anti-symmetrize, you will add it up too, so it 2 cancels. Okay? Such that you see that this is anti-symmetric. So m is anti-symmetric. Okay? That's the expectation. So what we have to do to actually compute it, to actually find out that Noether current, we just need to compute it. In particular, what we have to compute to construct this, you need to compute f hat function, right? So what is f hat for Lorentz? So basically you need to compute how this thing changes, and then you need to read out this thing, right? And then we can just write down the Noether's current. Let's do it. So you may remember the following. So U dagger lambda free scalar. This. Remember, I'm in the Heisenberg picture, or you can be in the Schrödinger picture, right? So in the Heisenberg picture, this, and then you should transform opposite. Okay. Right? So let's first work it out this, and then we're gonna work it out that, and then Lagrange. Right? So what is this? Inverse of x? Well, it will be minus omega x, because lambda I'm writing as 1 plus omega, so I'm gonna write this. So right now this is a small parameter, but at the end we're gonna just throw in the epsilon, okay? Just to get this unit object rather than the small object related by this. So I can now throw in indices. So x rho, I'm just gonna write it as that. Omega rho nu x nu. Okay? Or I can write it as basically I can up and down whichever way you want. Let me just write this. This is equal to rho nu x nu. I just lowered it. But then this is antisymmetry. I can also write it as a plus nu rho x down nu. Or if I want, I can do this too. Okay? No, that is violating law. That is illegal because I have to have up overall. I will not do that, but up to this point is correct. Also, you see why this is in general illegal, because depending on whether rho is a spatial time, there should be different sign here, right? Okay. So I can do this much. So I can create a magic that this is basically x plus a small quantity. Okay? So it looks like a special kind of translation. Are you with me? So this looks like small shift in x, but x dependent x. Okay? That makes sense because rotation doing this, right? So if you were here, you shift that much. You were there, you have to shift quite a bit. So it's a space position dependent translation. That's that. Okay, so then we can work it out this phi lambda inverse x as basically x plus delta x special kind, that particular kind, not random kind. So I know that this should be phi of x plus special kind rho phi. So let's put in this special shift. That's omega nu rho x phi. Okay? And so if I sneak in 1 epsilon, you understand that now my omega is unit quantity. Okay? Not in unit density. Okay, what about the Lagrangian? So Lagrangian, once again, is a function of x, right? So I can just work that out. You can take a harder way by actually varying with respect to phi and del phi, and then actually plug in everything. Or just you make use of the fact that Lagrangian is scalar function, Lorentz is scalar function as a function of space and time. So you can just do that. So this should be the same. L omega nu rho x nu derivative Lagrangian. So we want to find out this object. Now this object, I claim, first of all, I can pull out the derivative omega nu rho x nu Lagrangian. You might say, oh my god, what? So this is a constant. You say, yes, you can do that. What about that? Can we do that? Because if you hit this, what do you get? Metric. Metric is a symmetric rho nu. This is antisymmetric rho nu. So that gets rid of the problem. Are you with me? Yes? Do you see? Okay, so I did that, and then eventually I want to write it as a this. Oh, good. Before that, can I now switch up and down all the way through? Now I can do it. Everything is contracted, so like up and down I can do it. And then eventually I can write it as this. And then I need a one metric to take care of that row. Good. You run a lot of index. Done? Good. Now we can write down Noether's current to the Lorentz. All right. So current, or I have to write it as, yeah, why not? Let's write the current. What do you have to do? Do you remember still? Do you? Don't? No? So this? Is this new to you? Well, that's completely new. Let's do it. Okay, so this is that, right? And the F is this. Yes? Okay. Zoom out. Okay. I'm gonna pull out, what do you want me to pull out? I want to pull out omega new rho. Am I successful? Am I alone? It seems like. Oh. New. So I already lowered it. Okay? So I pull out these two common factors. Then what do you have? I have. Am I completely alone? Can somebody confirm that I'm not alone? Yes, I'm totally alone. Jeez. Are you with me? Good? Okay. Have you?
in this of
What?
that there row partial row is
Oh, up. You're complaining about this? Very good. So I'm not alone. So phew. Hello. Sticking to with me. Alright, are you with me? Okay. I already confirmed you. So do you recognize this object? Yes. So is this already completely new? Oh my god, that's a new world. I've never seen it in my life. So this is, we just talked about, this is energy momentum tensor, canonical version of energy momentum tensor. So, good. This is anti-symmetric. So what I can do is that I can have new row. Then I have to anti-symmetrize new and row, right? Yes? New, row mu, minus, row, new, mu.
여기 없으니까 that is
Not yet, which I don't have to. I'm literally anti-symmetrizing this and that. I'm not touching mu at all. So mu stays. I'm just anti-symmetrizing this, which I'm allowed to do. Okay? Good? And do you remember the expectation? So we wanted to get, even before, right? Even before we actually derived explicitly, okay, I wanted to have a Noether's current, but parameter is omega alpha beta. So for each alpha beta, I wanted to have some object which is conserved, which is antisymmetric, and that is that object. Okay? Alright. Now, so we now figured out what is this object, M. So let's actually take a look at it. Okay, so that looks like xt, antisymmetric, right? So let's actually look at a charge density. So let me just look at alpha, beta, charge density. Okay? So that is x alpha, t beta 0, x beta, t alpha 0, right? Okay. So now, let me remind you, recall, when we discussed the Poincare difference itself, we actually had a similar object, and let me define this to be J alpha beta. Just like in the context of a rho 0, I define this to be P rho. And then later we check the physics meaning of that, Hamiltonian density, and then P, right? We check the physical meaning of that. So we're going to do the similar job now. But in the Lorentz algebra or Poincare algebra discussion, we had this 4 antisymmetric tensor in 4 space and time, and then we talked about if I use a spatial component F, that gives us a generator for space-time, space rotation, angular momentum. And then we had a 0i, I0 up to important minus sign. That gave us notion of a boost. Okay? So that was what we talked about, in a very abstract level. But now we're talking about everything in terms of actual Lagrange formulation of quantum field theory, right? So let's check the physical meaning of this. Keeping in mind that we already knew this much. Okay? So I'm just gonna now evaluate that. So let's look at the spatial components. J, I, J of that object, which means M, I, J, 0. And what do you get? Xi, T, J, 0, Xj, T, I, 0. Yes? And so if you remember this, spatial component, this was, if you wish, momentum density. Okay, this is Hamiltonian density. So this is a momentum density. And so what does that look like to you? Well, this is still density. Remember, I'm looking at the charge density. In order to construct the charge, you have to integrate over the space. Yes, which I haven't done it yet. Is that correct? Well, I just realized. Nobody, you see, this is remarkable. Nobody tell me that there's a clock much closer than that one that I was having trouble with. Right there. Oh my God. Did you know this? Did you know who knew this? I'm not gonna pass on this. Did you know this fact that there's a clock right here?
I know that you're a practice. You are.
Oh, thank you. Okay, that somehow worked out. Although I was traveled all the time. I was like, what is that? Okay, 13. Let's push up. Okay, so this is a charge density, correct? So to get a charge, what do you have to do is you have to integrate this over the spatial volume, right? But let's just take a look at it. What does this look like to you? Doesn't this? So that actually, let's look it up. I, J, K, charge density. Let's actually compute this. And what do I get? I get, so if you contract epsilon I, J, K, that thing add up, right? It's 2 times epsilon I, J, K, X, J, P, K. Boom, boom. And that's what you would have called angular momentum density. Now this is a momentum density per volume, right? So this is angular momentum density. So perfect. So this is literally give you angular momentum density, and if you integrate over space, well, I don't know what to write. Is there a fancy word? Angular momentum, right? Okay, I failed. Usually this looks more like the density. So you work out, right? So this thing knows about it. This formalism knows about it. I see. What about the boost direction? That's angular momentum. What about the boost? Let's look at it. So what do I do? What do I do? Okay, let me just write it. J 0, is this what I want? I mean, up to minus sign, doesn't it? Right? So let's look at it. So this is T, and then I0 minus xi n t0, 0. So actually I wanted to look at that. Anyway, it doesn't matter. What was this? This was Hamiltonian, correct? And then this was momentum density. Yes? So if I integrate this, t I xi this. So first of all, time is independent from spatial integral, right? So I can pull it out, and then if you do it, you get actual free momentum. Okay, again, I screwed up. So boom, here's my momentum. Okay, and then there's some way to write it up. So what this is summing over energy weighted by x. Do you remember any operation like that? Have you heard of what's known as the center of mass? If you have a mass, you just compute the mass times length and then summing over that. They give you center of mass, right? Right? Yeah, very good. Then I can invent some notion of a center of energy, right? And then if I integrate that, that gives me a Hamiltonian. So this is center of energy, whatever that is. Okay, now, does that physically make sense? Does it? It does, at least in the sense that this is antisymmetrization of two spatial components, and this is antisymmetrization between temporal and the spatial. In that sense, that makes sense. You might say, oh, but that's hard, because you've never seen an object like that, right? You have seen an object like this, and it's called angular momentum, but you have not seen an object like this with any particular name in it. Now you know something. Okay, so that's that. That is that. Now, do I have time to talk about symmetry, operators, blah, blah, blah? Do I? Probably, it's better to stop here, because I don't think I can finish that. But anyway, so the plan is that now that we sort of have a formulation of a symmetry at classical level, right? Noether current, how to compute things. So next time we will not talk about not space-time transformation, but internal global symmetries. Okay? So we walk through all these key examples of that, both continuous, and then we will spend some time to talk about actually discrete internal symmetries. Not in discrete symmetries, in particular CPT. Okay, and how to think about those symmetries. Okay, so that's it for today. I actually have to run to some place right after this. I might be able to stick around, say, 5 minutes. Okay, so figure out ordering of the questions. I will stay outside, and then boom, boom, boom. We can address questions. All right, thanks.